Welcome to the deep dive. Today we're tackling, well, one of the really tricky challenges in building truly capable AI, getting it to understand and, reason about the messy three-dimensional world around us. We've got a fascinating research paper here introducing a new system. It's called VDAR, that stands for Visual Agentic AI for Spatial Reasoning.
That's right. And, we see incredible progress with AI these days. I mean, especially with these big vision language models like GPT-4o or Gemini. They can look at an image, tell you what's in it. They recognize objects, the categories, understand basic facts. That's sort of the seeing part, the semantics.
Yeah, exactly. They know a chair is a chair, a table's a table, simple stuff. But our source paper points out something really crucial here. Their ability to understand spatial relationships, in the real 3D world. That's where things get, well, they get really shaky. Their performance significantly declines. That's the paper's wording.
And that's really the heart of the problem VDAR is designed to solve. It's not just about recognizing the objects anymore. It's about understanding where they are relative to each other in 3 dimensions, their actual physical size, the distance, orientation, all that stuff. Think about like a robot trying to navigate your living room. It needs more than just labels like chair, table, couch. Helps. It needs to know the couch is in front of the window, maybe the table is to the left of the chair, and crucially, is the gap between them wide enough to actually fit through.
Okay, yeah, that makes sense. So why is this 3D spatial reasoning just so fundamentally hard for current AI? What's the hang up?
Well, because it requires more than just, simple pattern matching. It involves these complex, multi-step reasoning processes. You have to first ground your language, link words like the big book or the red chair to specific pixels, specific regions in the image. That's step 1. And then you need to perform inference, apply logic, and maybe some world knowledge to those grounded elements. The paper gives a great example. It really nails this. Trying to figure out the radius of a mirror in a scene. But not by seeing the radius directly, no. It's based on comparing its size to the known height of a table that's nearby in the picture.
Oh, okay.
You have to understand scale, depth, relative size, all in 3D space. Current models, they often stumble badly on these kinds of questions.
Right, right. It's like asking you to measure something way across the room just by looking at a photo, and maybe you only know the height of one other thing in the picture. You need a way to relate sizes and distances in that 3D scene somehow. Now, the paper mentions that previous attempts to tackle these complex visual questions often try to break the problem down, maybe by generating computer programs to process the visual information, methods like Viper GPT or ViceProg.
Exactly. Those were definitely steps in the right direction.
Good.
Trying to tackle complex tasks by breaking them into logical steps, steps executed by code. Smart idea. But the key limitation, this is what the paper highlights, was that they relied on a static, predefined set of tools.
Static, meaning fixed.
Yeah, fixed. They had a fixed library of functions like an API or maybe a specialized programming language that was decided beforehand, by humans.
So if the problem required a tool that wasn't in that pre-approved box, they were just stuck.
Precisely. That static nature, it severely restricts the range and the complexity of problems they can actually solve, especially when they're faced with novel scenarios, or maybe questions that just weren't anticipated when the toolset was originally built.
Okay. So this is where VDAR comes in with its big academic innovation, right? It doesn't use a static toolset.
This is where VDAR gets really interesting and, academically significant.
Yeah.
It introduces a genuinely novel approach. Instead of that static, predefined stuff, VDAR dynamically generates its own tools.
Whoa, wait. Dynamically generates its own tools?
Yeah, it built a custom API of functions, essentially learning new skills on the fly based on the questions it's actually trying to answer.
How does it even do that? That sounds complicated.
Well, the paper describes it as an agentic program synthesis framework.
Yeah.
Think of it like a collaborative team, a small team of large language model agents working together.
Agents. Like little AI workers.
Kind of, yeah. They're not just answering questions, they're acting like a mini software engineering team. One agent defines the need for new functions, another agent runs the Python code for them, and then a third agent tests that code to make sure it actually works correctly. It's defining, implementing, and testing solutions, all dynamically.
Huh. That's a huge shift. It's not just using existing code snippets someone else wrote. It's writing entirely new functions tailored to the specific problem domain it encounters right then. And this dynamic capability, that's what allows it to handle that wider range of complex queries the paper talks about.
Absolutely. By not being limited to a fixed set of skills, VDAR can synthesize programs for situations that those static API methods just couldn't handle. It's a core technical innovation, no doubt.
And the paper also points out that VDAR is training free. in a specific sense. What does that mean here? Is it really no training?
Well, training free here means it doesn't require those huge supervised data sets of image question-answer pairs that specifically include complex 3D information. Some other approaches, especially neurosymbolic methods or maybe fine-tuning large VLMs just for 3D, they need massive amounts of this specially annotated data. And that stuff is incredibly expensive and just really difficult to get for real-world 3D scenes. Vadar avoids this dependency.
Which has big implications for scalability, I guess, for applying it to new situations.
Exactly. Major implications for its scalability to new, complex domains where you just don't have that kind of labeled data.
Okay, let's really dive into the how then. This agentic architecture sounds complex, but super interesting. The paper breaks it down into two main phases, API generation and program synthesis. Tell me about that first phase. How do these agents actually build this custom toolbox?
Right, phase one. This is really the heart of the innovation, creating those new dynamic skills. It involves three key agents working together. First, you've got the signature agent.
Signature agent. What's its role?
Okay, so it receives a batch of questions. And importantly, just the questions, no answers provided.
Yeah.
Its job is to look at these questions and propose general method signatures. Think of this like defining the purpose of potential new functions.
Like function blueprints.
Kind of, yeah.
Yeah.
Okay, based on these questions, we might need a function to find the size of an object, or maybe we might need one to calculate the distance between two objects. It identifies these subproblems implied by the questions and suggests function definitions, the signatures, for them. And interestingly, the paper found it actually works better without in-context examples for this step.
Really? Why is that?
Because it encourages it to propose a more diverse and novel set of potential methods. Less constrained thinking, maybe.
Okay, so the signature agent figures out what functions they might need. Then the implementation agent steps in.
Exactly. The implementation agent takes those signatures proposed by the first agent and writes the actual Python code for those functions. And what's quite sophisticated here is that it can write new functions that call other functions that have already been implemented and added to the API.
Ah, so it can build skills hierarchically, like layer them.
Precisely, building on top of existing pieces in its growing toolbox. So a function to calculate, say, the area of something might call a lower-level function that finds the object's dimensions first.
Makes sense. Building blocks.
Right. And the paper notes this agent does benefit from some examples, specifically weak in-context learning examples, not full solutions, but just demonstrations of how to implement basic visual methods. Gives it a nudge.
Got it. And the third agent in this skill building phase is the test agent. This sounds critical for making sure the code isn't buggy.
Oh, it absolutely is. The test agent is basically a Python interpreter running in the background. As soon as the implementation agent writes a new method, the test agent tries to run it, but with placeholder inputs, just to catch any immediate runtime errors.
Like a syntax check or basic logic check.
Yeah, exactly. If there's an error, it provides feedback the Python exception itself back to the implementation agent, which then attempts to fix the code. It's an iterative loop.
Okay, so they write code, they test it, they fix it if it breaks. Standard enough. But what about dependencies? What if a new function calls another function that hasn't actually been written yet?
Ah, yeah. This is where the test agent's role gets particularly clever, and it really highlights the academic novelty of this agent collaboration. If the test agent tries to run a newly implemented function and finds it calls some prerequisite function that doesn't exist yet in the API, it signals the implementation agent to basically pause what it's doing and go recursively implement that prerequisite function first.
Recursively, so it dives down to build the foundation first.
Exactly. It's like building a dependency tree on the fly, using a depth-first approach. It makes sure all the necessary components are built and tested before the function that needs them can be finalized and tested itself.
Wow. Okay, that's really smart. So they're not just building a flat list of functions, they're dynamically building and validating a whole interconnected library of skills, making sure everything needed is in place. That's phase one, API generation. What happens in phase two, program synthesis, the actual problem-solving part.
Right, so once that dynamic API is built, based on that initial batch of questions, the system moves on to answering a specific question using the newly created toolbox. This part is handled by the program agent.
So the program agent gets the custom-built API that was just generated and the single query it needs to answer now.
Precisely. Its task is to generate the final Python program, basically, a sequence of calls to the functions in that dynamic API that will solve that specific query. The paper mentions it uses chain of thought prompting here.
Ah, SUOT to help it plan.
Yeah, helps it think step by step and plan out the logic before actually writing the code that calls the API functions.
And the last piece of the puzzle is the execution agent.
Yep, another Python interpreter. It takes the program that the program agent just generated and runs it line by line. And just like in phase 1 with the test agent, if there's an error during this execution, maybe the program tried to divide by 0 or, I don't know, called a function incorrectly, the execution agent provides that error feedback back to the program agent.
Which can then try again, regenerate the program.
Exactly. It can attempt to generate a corrected program.
So it's this really sophisticated, self-correcting, collaborative process between these AI agents. They're figuring out what tools are needed, building them, testing them, and then using those custom tools to solve a specific problem. And with error correction loops at both the building stage and the execution stage, this feels like a major academic departure from just prompting one giant model or using some fixed visual programming language.
It really is. It's breaking down this incredibly complex task into subtasks handled by specialized agents. And it's focusing on that fundamental problem of tool creation and utilization dynamically.
Okay. Now, the programs generated by Vadar use this custom API, right? But that API still needs to actually interface with the visual data, with the image itself. The paper talks about underlying vision specialists. What are those exactly? What's doing the actual seeing?
Ah, yes. Good point. The dynamically generated API functions, they represent the high-level reasoning steps, but they ultimately rely on lower-level perception models to extract the raw information from the image. The paper lists several standard sort of state-of-the-art vision models used as these specialists. They use, let's see, Molmo's pointing model and grounding Dino for object localization, finding where things are. That's locked in their API. SAM, the segment anything model, is used to get the 2D size of detected objects, get to object size. Unidepth provides depth estimation.
So these are like off-the-shelf vision tools, and even GPT-4o, which we talked about as a big VLM earlier, it's used here just as one of these tools.
Yeah, exactly. In this Vadar architecture, GPT-4o acts as just one specialized module. It's used as a visual question answering module. They call it VQA. Its job is just for simple attribute queries after an object has already been located, like asking about its color or maybe its material. Simple stuff. There's also a basic internal function they wrote, same object, just to check if two detected points likely belong to the same object, probably based on bounding boxes overlapping.
I see. So these are the fundamental perception building blocks that Vadar then orchestrates with its dynamically generated code.
That's the idea. High-level reasoning, orchestrating low-level perception.
Okay, they've built this really innovative system, collaborating agents, dynamic API generation. Very cool. How do they actually test if it works better than the older methods, especially on those tough 3D reasoning problems we started with?
Right, the evaluation. They tested Vadar on some challenging benchmarks. First, there's the classic C-Lover dataset.
CLER, yeah. Synthetic images, but known for testing complex reasoning.
Exactly. It's synthetic, but it tests compositional reasoning, combining different skills very effectively. So it's a good starting point.
And the paper introduces a brand new one too, right? OMNI 3D Bench. You mentioned this is a big contribution itself.
Yes, and this is really important. ONNI 3D Bench is derived from the Omni 3D dataset, and it features images from real-world indoor scenes. Think kitchens, living rooms, offices. And it comes with rich 3D object annotations. But what makes it extremely challenging, as the paper puts it, is the nature of the queries.
How so?
They are non-templated, free-form, natural language questions, not just fill-in-the-blank stuff. They often require understanding really complex 3D relationships like relative depth, is object A behind object B, size comparisons in 3D, not just 2D pixels. They even include hypothetical scenarios. This makes it much, much harder than datasets like GQA, which tend to rely on simpler template-based queries or focus more on just 2D appearance or single reasoning steps.
Okay, so they're testing it on both synthetic complexity with Clever and real-world messiness and complex language with OMNI 3D Bench. Smart. So what did the results actually show? Did Vadar's fancy dynamic approach pay off?
Well, yeah, the benchmark results clearly demonstrate the power of this dynamic API approach. The paper states, Vadar outperforms Viper GPT and Visprog with a big margin.
A big margin. How big?
Over 20% improvement on both Clever and OMNI 3D Bench compared to those static API methods.
Wow, okay. That's substantial.
It really is. It directly validates that core academic hypothesis. Dynamic skill generation is superior to static toolsets for handling a wide variety of complex visual queries.
Okay, so it beats the older program-generating methods. How did it stack up against those big monolithic VLMs like GPT-4o that can just look at an image and answer?
That's maybe even more interesting. Vadar is competitive, which is pretty impressive given its fundamentally different, more modular approach. On Savor, it actually slightly edges out the big VLMs on question types that require deeper, multi-step reasoning. On the very difficult OMNA 3D bench, it performs strongly. It demonstrates its ability to handle that complex spatial reasoning in real-world scenes. It was narrowly behind GPT-4o overall, but significantly outperformed other large VLMs by over 5%.
So comparable performance, but Vadar has another advantage you mentioned, interpretability.
Exactly. While the raw accuracy is competitive, Vadar provides this major practical advantage. It generates interpretable programs. You can literally look at the Python code Vadar wrote to answer a specific question and understand the step-by-step logical process it followed. That's huge compared to the sort of black box nature of the giant monolithic models.
Yeah, that interpretability is massive for building trust, for debugging, for understanding why it got something right or wrong. But you said there's an even deeper insight from the performance numbers, something the paper calls oracle accuracy. Tell me about that. That sounds fascinating.
Ah, yes, the Oracle results. This might honestly be the most academically revealing finding in the whole paper. Oracle accuracy is basically a hypothetical simulation. They run VDAR, but they pretend its underlying vision specialists are perfect.
Perfect, meaning they always get the location, size, depth exactly right.
Exactly. They essentially feed it the ground truth information for object location, size, depth, etc., instead of relying on the real, potentially noisy output from models like SAM or Unidepth.
So it's testing the reasoning part in isolation, assuming perfect eyes. What happens then?
Well, if its eyes were perfect, Vadar's accuracy just jumps dramatically. On Sleever, it hits 83.0% accuracy.
Okay, big jump. What about the real-world benchmark?
On the challenging OMNI 3D bench subset they focused on, it reaches 94.4% accuracy with Oracle Vision.
94%. Wow. So, wait. That means the AI's reasoning engine, the part that generates the program, the logic, the agent collaboration, that part is actually performing near perfectly already.
Pretty much.
The real problem holding it back isn't the thinking, it's the seeing. It's the accuracy of the basic perception, the object detection, the depth estimation.
Exactly. That's the crucial insight here, I think, for the whole field. It strongly suggests that for these complex spatial reasoning tasks, the main bottleneck isn't necessarily the high-level reasoning capability or the ability to generate complex logical programs. It's the fundamental accuracy of those low-level perception models that provide the raw data about the 3D world.
That's huge. It really points future research in a clear direction, doesn't it? Focus on improving those specialized perception tools.
Absolutely. Make the eyes better, and the brain can already do amazing things.
And going back to that training-free aspect we discussed, how did that play out in the results compared to methods that do need lots of specific 3D training data?
Right, the scalability advantage. Yeah, that showed up clearly too. The paper shows Vadar, which, remember, only uses a small set of questions to guide its API creation, not supervised 3D examples, significantly outperforms methods like Left. Left does require extensive domain-specific 3D training data. Vadar beat Left, even when Left was trained with up to 10,000 supervised examples on Sleeter.
10,000 examples, and Vadar still won without them.
Yep. And even more telling, Left couldn't even be evaluated on the real-world OMNI 3D bench. Why? Because that kind of specific large-scale 3D training data simply wasn't available for that data set.
So Vadar's training-free nature makes it much more adaptable to new real-world situations where you don't have perfect labels.
Exactly. Much more practical for scaling up.
Okay, so summing up the wins, lots of innovative technical pieces, the agent collaboration, the dynamic API, strong performance validating that dynamic approach, and this critical insight about the perception bottleneck being the main issue. What about the downsides? What are the remaining limitations? Where does Vadar still struggle?
Yeah, the paper is quite upfront about Vadar's current struggles.
Yeah.
For one, it sometimes falters on queries that require a really long chain of reasoning steps.
How long is long?
Say 5 or more inference steps. This suggests that while the framework is powerful, pushing the boundaries of really extreme logical depth is still a challenge for the current agent setup.
Okay. And obviously, as we just discussed, the overall performance is ultimately capped by the accuracy of those underlying vision specialists. The Oracle results proved that.
Right. That's definitely a limitation of the current instantiation of Vadar, even if, as you said, it points to a clear path for future improvement across the field. Improve the specialists, Vadar gets better. The paper also notes one other thing. Vadar currently generates the program based only on the text query. It only incorporates the actual visual information during the execution stage when the program runs.
Ah, so the program writing is blind to the image.
Essentially, yeah. They suggest that incorporating some level of visual awareness during the program synthesis phase itself, that could potentially help. Maybe help with handling more complex scenarios or reasoning about visual properties that need to be inferred directly from the image before deciding the program structure.
Makes sense. Those limitations sound like pretty direct pointers for future research directions then. Refining the agent interactions for deeper reasoning, improving that vision layer, maybe making the program generation itself more visually aware.
Exactly. This paper lays a really strong foundation, I think, and clearly highlights where the next breakthroughs need to happen. It's good science.
Okay, let's wrap this deep dive up then. Vadar represents a significant academic step forward in getting AI to reason about 3D space. It moves beyond those old static tools with this novel agentic framework that dynamically builds its own API of skills as needed.
Yeah, it's a training-free, highly innovative approach using these collaborating LLM agents to define, implement, and test new functions on the fly. And it showed really impressive results on tough benchmarks, including that new real-world OMNI 3D bench they introduced.
And maybe the breakthrough insight, the one that really sticks, comes from those Oracle accuracy experiments. It tells us the core reasoning and the program synthesis abilities. They're actually pretty robust already. The main barrier holding back performance right now is the accuracy of the underlying perception models, the things feeding it information about the 3D world.
Right. This research really makes a strong case that for complex tasks like 3D spatial understanding, the path forward might be less about building one single massive general-purpose model that tries to do everything. And maybe it's more about creating intelligent systems that can orchestrate teams of highly capable, specialized components, where you have intelligent agents doing the reasoning and building the logic, and specialized perception models providing the necessary, hopefully accurate, raw data from the world.
So this deep dive into VDAR leaves you, our listener, with a final provocative thought to chew on. If the bottleneck for complex AI tasks like navigating and truly understanding the 3D world is less about thinking perfectly and more about seeing perfectly, does the future of AI lie primarily in perfecting its senses, or does it lie in building ever more intelligent conductors like VDAR's agents that can expertly leverage whatever imperfect senses are available today and tomorrow? Something to ponder.